This lesson deals with ideal diode circuits. You can find these notes in the ECE302 ebook in Chapter 2, starting at the bottom of page 3. In our last video, we introduced an ideal diode, and this is the symbol for it. And we interpret the symbol as the following. Current can flow in this direction, but it can't flow in this direction. That's sort of what the bar is saying here. And when current flows in this direction, this looks like a short circuit. And when current flows in this direction, it looks like an open circuit. In other words, no current will flow. Given this circuit with two ideal diodes, two resistors, and two batteries, and assuming this is a practical circuit, can you find the current I sub S by guessing at the states of diodes D1 and D2, and then check your guesses to make sure that you found the correct states. The assumed states analysis technique is taking a guess as to the state of the diode and then seeing whether the results are consistent with the guess. Let me just take wild guesses and then we'll talk more about a strategy in a little bit. Suppose I assume diode D1 is off, or it's an open circuit, and diode D2 is on, or a short circuit. So we're going to replace the diode, which was between this node and this node. And this is where the anode was, and this is where the cathode was of diode 1. I'm assuming that it's an open circuit, in other words, it's off. Label the voltage across it. The current through it is 0 by definition. For diode 2, assuming that it's on, it's a short circuit, but the anode was here and the cathode was here. I'll label the current from anode to cathode. I'll label the voltage here being 0 because by definition of a short circuit, that's 0 volts. Then we're going to analyze the circuit and solve for the current ID2 and the voltage VD1. I like to write down as much work as I can on the schematics. Let me do that. Because this current is 0, that means the current in this resistor is 0, and then by Ohm's law, 4,000 ohms times 0 is 0 volts. I'll call that my step number 1. To find the voltage across this diode now, I can just find the two node voltages and take their difference. This node voltage back to ground is minus 0 plus 10, and that's this number right here. And then from here, I have a battery, so here's plus 3 to ground, but I'm going to subtract this node, so minus 3. So I get 7 volts. This to be an open circuit, the voltage across here needs to be less than or equal to 0. But 7 is greater than 0, and so that's a contradiction. I'll use a little asterisk to indicate that there's a contradiction. You could stop right now, but let's solve for ID2 to get some practice on basic circuit analysis. Here I've got a battery, and I've got a resistor in parallel, and the current in this resistor is the same as the current coming out of the battery, which is the current in diode D2 from anode to cathode. 3 volts divided by 6K is 500 microamps, and that is greater than or equal to 0. So this was not contradicted, and this was in the correct direction. It was greater than or equal to 0. So since this was contradicted, let's just change this to the opposite state, and let's make it a short. That would seem logical. Let's analyze this circuit. We still have the short for diode 2, but for diode 1 now, we're going to put a short circuit. Again, anode to cathode, current's going to flow in this direction, and then that's going to be our I sub D1. The current that's flowing in here is the current in the resistor, and that's going to be this node voltage minus this node voltage. 10 volts minus 3, which is this node voltage here, and then dividing that by 4K, I get the current in the resistor, which is the same as the current in the diode, and that's 1.75 milliamps. And that is greater than or equal to 0, so that's great. Let's just check the second one. Now I've got this hooked up here, and the current in the diode is related to these other two currents. Let's find the current in this resistor since it's still in parallel with this 3 volt source. So 3 divided by 6 is still 500 microamps. So I'll put it in milliamps because I've got this one in milliamps. I like to write Kirchhoff's current law in just one line if I can. I'm solving for ID2, and that's entering the node. And that will have to equal what leaves the node. Leaves the node this direction, and what leaves the node this direction. Obviously this is I sub 6K, and this is in the opposite direction of ID1, so it'll be the negative of it. Do Kirchhoff's current law in just one quick step. Take the second result minus the first, and I get a negative 1.25 milliamps. But for this diode to be a short circuit, the current ID2 needs to be greater than or equal to 0. So that's a contradiction. So that's not correct either. Let's just try the opposites. Let's have both diodes off. Replace diode 1 by an open circuit. Here's the anode and cathode of diode 1. So that's where my voltage V sub D1 is. And then, of course, here's my diode 2 from the anode to cathode and V sub D2. Let's write down anything we can in the drawing. Because this is an open circuit, there's no current here. There's no current here, so the current in here is also 0. So that's my first step. And 0 current times 6K is 0 volts. Also, the current in here is 0. The current in here is 0. So 0 times 4K is 0 volts. Do this differencing of these two node voltages to get the voltage across diode 1. Just go from here back to ground, get minus 0, plus 10. And then from here, go back to ground this way. I don't know the voltage across the open circuit. I do know the voltage across this resistor, so it's going to be minus 0. And that's equal to a plus 10 volts, and that's a contradiction. Yeah, we could stop here, but let's solve for the other one just to get some practice. This node voltage is 3. This node voltage is 0. 3 minus 0 is 3 volts. But that also is a contradiction. This needs to be less than or equal to 0. The last case to try is a short circuit here and an open circuit here. In other words, diode 1 is on and diode 2 is off. Label the anode and cathode again. That's the direction of current for diode 1, and then the anode and cathode for the polarity of the voltage across diode 2. Because this is an open circuit, the current that flows in here is the same in all the elements. 10 volts divided by 10K would be the current that's flowing in this loop, and that's 1 milliamp. And that is greater than or equal to 0. The voltage here is 3 volts. The voltage here I can calculate because that 1 milliamp flows into here. 6K times 1 milliamp is 6 volts, and so I get 3 minus 6 volts, or minus 3. And that is less than or equal to 0. This is a consistent set of results with our guesses, so that is the answer. Now we can solve for whatever we want to in the circuit. In the original problem, I asked you to solve for the current I sub S, which is the current in diode 1, and that's 1 milliamp. We do this in circuits to calculate how long a battery will last. That's the current coming out of this larger battery. And so there's a technique for doing that. That's actually in the ECE302 lab. Suppose that the fourth guess didn't work. Well, something's wrong. The diodes have to be in a particular state. It's either short or an open. There were 4 possible things here. One of those 4 has to work. In fact, only one of the 4 can work. If all 4 don't work, you made an algebraic mistake. In the first case, we had diode 1 off and diode 2 on, and then on, off, and then on, off. There are 4 cases here. If you think back to ECE230, where we talked about digital circuits, we can talk about the number of combinations of things. With 2 diodes with 2 states, there's 2 to the n possibilities. So in this case, 2 to the 2 is equal to 4. If we had 3 diodes, it'd be 2 to the 3, or 8. And you can see it explodes very quickly. Is there some way that we could take a better guess on our first shot? We'll take a look at it in the next page as a strategy for guessing. Now in the ebook, you'll see that there is a bookmark called Supplemental Problems. These are old homework problems that I gave in ECE302 years ago, and they're good practice problems for playing with the ideas we just talked about. And these are also listed in the paste for the course with the videos, but if you just are looking at the notes by themselves, you can look at the bookmark and see that once we've covered page 5, then you can do these 2 supplemental problems. Let's take a look at a strategy for guessing the states of the diodes. Let's go back to the ideal diode again and think of it as a resistor. It has 2 possible values, the short circuit and the open circuit. In other words, 0 ohms and infinity ohms. Putting in 0 or infinity in an equation, sometimes you get funny results. Just think of this as a low resistance and this is a high resistance. Or maybe think of this as a milliohm and maybe this is a gigohm. So if I took a look at my circuit and put a resistor into the circuit where the ideal diode is, then we could analyze the circuit and see which way the current is trying to flow. And then based on that, we could take a guess as to whether the diode looks like a short circuit or an open circuit, or a low resistance or a high resistance. Here's our example that we had previously. And let's replace diode 1 by a resistor and show the current flowing from anode to cathode. The same thing for diode 2, from anode to cathode. Okay, so here I got a circuit with 4 resistors and 2 batteries. As I mentioned previously, let's consider this to be a practical circuit. What I meant by that is that this isn't a trick circuit where I'm picking numbers so something funny happens. And in a practical circuit, if you have multiple batteries, usually the biggest battery is the one that generates power because you don't want to put multiple battery packs into a circuit. We'll look later in the chapter and see there's a way to create a battery that only absorbs power with a thing called a Zener Diode. I want to assume that this battery generates the power for the circuit. That means that current comes out of its plus terminal. Now resistors can only absorb power, so we can deal with that also as we analyze the circuit. Hook this circuit up, and we assume that this generates power, and that's assuming also then that this is going to be absorbing power. Current's going to come out of this battery and have to come back to the original battery, and likewise some current's going to have to flow back over here. And I've shown this on the bottom of the page. So I'm guessing that the current wants to flow in this direction and this direction in the circuit. What does that mean? That means the current wants to flow from anode to cathode for diode 1, so I would guess that it's a short circuit. And for the second diode, it's wanting to flow from cathode to anode, which would imply that it's a high resistance, in this case an open circuit. Now that did match up with our guesses that we did previously. I'd guessed intentionally 3 wrong before I got the right one. Now this technique doesn't always work, but it might get you closer on the first guess. There really is no method that you can come up with because these are nonlinear circuits. What we can do is, again, use this strategy to get close to a result. Let's take a look at an example of a transition state. In this last example, we had a battery here of 3 volts, and that caused diode 1 to be on and diode 2 to be off. What would happen now if I were to increase the value of that 3 volt battery such that diode 2 started to conduct? Now in electronics we calculate things like that because we use detectors to turn on something, whether it's a light or an alarm system, if something happens. Transition points allow us a way to find out where that's going to happen. Let's put diode 2 from its state of being off to the transition of just going from off to on. Now that means that the voltage across it is 0 and the current through it is 0. Now we don't have a symbol for that in our circuits course so far, and so we're just going to label it on the drawing. Now what we've done is we've gone from a case where I had no current here before, and now I'm going to have no voltage. So I'm actually over-specifying the circuit. I need to back off on one variable, whether it's a resistance value or a voltage. Here it's V sub S. If I don't do that, I'll get an inconsistent set of results or no results. Let's analyze the circuit now with this being at the transition point and see what value of V sub S would make that happen. And we also have to check that diode 1 is still in the original state that we thought it was in. Let's just check that too. I have no current here, and so the current that's flowing in here is I sub S, which is also I sub D1, from anode to cathode, back through here, back through here. So the rise in voltage is 10, the drop is I sub D1, or I sub S, times 4K, and then just that same current, because there's 0 here, times 6K. So I can solve that then for the value of ID1. It's like before, it's 10 volts divided by 10K, or 1 milliamp, and that is greater than or equal to 0, and so that checks. I'll solve for the value of V sub S. The rise in voltage here equals the drops around the loop. A drop in this direction from the 1 milliamp times the 6K, or 6 volts. The rise in voltage equals the drop of 0 plus 6. I get a value of 6. So when this battery is lifted up from 3 volts to 6 volts, now both diodes are conducting. This was no specific application, but it was an example that was in a book I used years ago that I really liked because it showed these ideas of assumed states and the idea of the transition point or transition state. And these are some examples of ideal diode circuits.